Hi everyone. So this is my first video for the Matlab class, and it's a bit interesting because we are finished talking about content for Matlab. I'm not introducing anything new, I'm just providing examples for the things that we've done in the past to help illuminate points that are necessary for the take-home exam. So there are two questions in particular that I expect to field a lot of more fundamental questions on. That's the second question about using finite difference schemes, ordered delta t to the fourth accurate schemes over a set of data of your choosing. I kind of expect to field questions about that, and I'm not talking about that in this video. Also, the last question, which gives you a complex ODE system and asks you to plot the result, basically. That's the one that I expect to get the most questions on. It's actually not that challenging of a problem overall. I'll talk more about it as we move along. One of the big challenges in that problem is just writing something as a system of equations, essentially, a system of ordinary differential equations, which we can use to solve using Matlab, or use Matlab to solve, I should say. To help illuminate that problem, I'm actually going to solve a completely different problem. I'm going to solve a completely different problem using Matlab, and it's going to be similar in principle, but different in the details. So the problem I'm going to look at is specifically an object flying through the air. If you have an object that is currently moving through the air with velocity v, it is subject to Newton's second law of motion. That Newton's second law of motion is that the sum of the forces is equal to the mass times the acceleration of the object. So I'm going to draw a free body diagram to consider the forces acting on this object. There are two forces acting that we're going to consider. The first force is gravity, so we have a weight force. I'll draw that on my free body diagram. It simply points downward. It's equal in magnitude to m times g, where m is the mass of the object and g is the acceleration due to gravity. I want you to think of this as a vector with magnitude and direction. The magnitude is given here, and the direction is given by the arrow. It's clearly pointing downward. The second is atmospheric drag, or maybe I'll say aerodynamic drag. I like that a little bit better. Let's call it that. Aerodynamic drag forces. We're going to use a simple model for this. It's just going to be a ball. It's going to produce no lift. It's just going to have drag on it. And the general formula for the atmospheric drag force, or the aerodynamic drag force, is that the drag is equal to 1/2 times the density of the air times the speed of the object squared times the generally cross-sectional area and the coefficient of drag. Okay, so in this, S is a cross-sectional area. The coefficient of drag, generally speaking, has a single value for an object of a certain shape. So we're going to use a spherical object, and we're going to use a coefficient of drag appropriate for that object. The coefficient of drag we'll talk about a little bit more in just a moment. Rho is the air, or I should say perhaps fluid density. I don't want this to be confusing. People often think that fluids are liquids, and that's not true. Air is a fluid, so in this case we're talking about air density. And everything else there is pretty clear. I'll be explicit though. V is the speed of the object. That is speed relative to the air that it's moving through. Well, I shouldn't say air, I suppose I said fluid earlier. I should say fluid again here. So in this problem, I'll just say this. Aerodynamic drag is in general quite complex, and most of that complexity is hidden in this term here. The coefficient of drag handles all the additional complexity. The coefficient of drag can depend on a wide variety of factors. We generally simplify a problem to just give it a single numerical value for a certain shape. In reality, the coefficient of drag depends on lots of things: size and shape and speed, actually. But we're going to just simplify it. This is, you might notice, not a vector. As written, this is simply the scalar drag force. That is, how large is the drag force. Which direction does the drag force point? The drag force in general points in a direction opposite the velocity. The velocity vector points in one direction and the drag force opposes that motion. It doesn't matter which direction you are accelerating, it only matters which direction you're currently moving. So I'm going to go ahead and make this a vector by multiplying it by the velocity vector divided by the velocity vector's magnitude. This is now a vector. Oh, sorry. Right now the drag force points in the direction of velocity. I probably don't want that. So I'll throw a negative sign out in front to indicate that this points opposite the direction of velocity. I'll draw that on my picture. The velocity is currently drawn up and to the right, so I'll draw the drag force down and to the left. I will label it with a little d. And if I'm going to write this out as Newton's second law, I'm going to write it in, well, I don't want to necessarily say component form, but I guess I will. Component form. So let's think about the component form for Newton's second law. Newton's second law says the sum of the forces, which is equal to the drag force plus the weight force, is equal to mass times the acceleration vector. If I think about the components of this, let's write it out as written, but when we see a vector, we'll write it in terms of its components. So I will say this is equal to -1/2 times rho times v squared times s times cd. I'm going to regret that. Let's take a moment. I'm going to actually take the v and move it to the right side of the equation. We'll just talk about why in just a moment. So 1/2 rho times s times cd times v squared times v divided by the magnitude of v. I want to point out this is the speed of the object and this is the magnitude of the velocity vector. Hopefully we can all recognize those are exactly the same thing. So I'm going to go ahead and point that out on the right side. V is just the magnitude of the velocity. Speed, of course, is magnitude of velocity. So I'm going to both, one, simplify this as well as stop using this symbol because it's, quite a bit to write. So let's go ahead and rewrite this expression. V squared divided by v is just v. So I will go ahead and erase all this and write it as v times the v vector. Okay? And then the v vector I'm going to replace with its x and y components. It's a vector. We're going to do it in 2 dimensions. So this is vx comma vy. And it's also worth pointing out that this right here can also be put in terms of the components of v. So I'm going to. I don't quite have enough space for it there, so I'll just put a multiplication symbol. This is then times the square root of vx squared plus vy squared. That is how we find the magnitude of a vector. So this is all the drag force. The weight force, well, that's pretty easy. It points in mg, and then it's just actually negative j hat. It's all straight down. So I'm going to go ahead and write this in the following fashion. This vector is plus the vector 0, comma, negative mg. So this is the problem in vector form. Vx equals, well, let's just say, I could write this in components if I wanted to. The first component of the first, the left, what shall I say? If I write this all in components, I have the following vectors. Negative 1/2 rho SCD root Vx squared plus Vy squared times Vx, comma, negative 1/2 rho SCD square root of Vx squared plus Vy squared Vy minus mg. These are the x and y components of the vector force. And they are equal to the mass times the acceleration. I'll write m, the acceleration, which is equal to m times ax comma ay, which I can write that all in the vector max comma may. Cool. This is me writing Newton's second law in component form for an object flying through the air with an aerodynamic drag force and the weight force. The only difference between this and projectile motion is that for projectile motion, both this term and this term are not there. They are 0, and you just have an acceleration of g downward. But here we have all this other stuff too. I'm going to go ahead and copy this equation to the following page. Do I actually want to copy it all down? Not so much. I'm going to write, yeah, I suppose I will. Here we go. Negative 1/2 rho SCD root Vx squared plus Vy squared times Vx, comma, negative 1/2 rho SCD square root Vx squared plus Vy squared times Vy minus mg equals max may. This, believe it or not, is a differential equation, and it's a system of differential equations, in fact. You could say it's a vector differential equation. I'm going to say it's a system of scalar differential equations because that's what Matlab can actually solve. Because it's worth pointing out that the derivative of the x position with respect to time is the x velocity, and the derivative of the x velocity with respect to time is the x acceleration. And likewise, the same is true for y. dy dt equals vy, and dvy dt equals ay. So we have, if we want to think about position, two derivatives up here. I can put everything in terms of x, let me say this, vx equals x prime, ax equals x double prime, vy equals y prime, and ay equals y double prime. So I can put all of this stuff up here in terms of these quantities. It's a second order system because I can express x double prime in terms of only x prime, y prime, x, and y. And t is allowed as well. If I take this expression up here, this big expression, can I solve for x double prime? Remember, x double prime is this. So yeah, I'm just going to look at the x components of this equation. I'm going to solve for ax. Ax is equal to 1 over m times negative 1/2 rho c ds square root x prime squared plus y prime squared times x prime. That's it. And y double prime is equal to 1 over m times minus 1/2 rho c d s square root x prime squared plus y prime squared y prime, oops, missed one thing, minus mg. I have the second derivative of x and the second derivative of y in terms of x prime and y prime. If you know a higher derivative in terms of only lower derivatives, then you have a differential equation. This is a differential equation, believe it or not. But now I need to make a choice for Matlab where this is written as, first of all, a first order differential equation, and second, only in terms of one variable. One vector variable may be, but one variable nonetheless. So I'm going to make a change of variables. I'm going to call y a vector, and it's going to have the following components: x, y, x prime, y prime. I know I have a differential equation in terms of x double prime, y double prime, so I'm going to make a choice for my vector that contains all the things that are in the expression up here, that when I take a derivative, I get these things. And I sure will. Y prime is equal to x prime, y prime, x double prime, y double prime. And I can put these in terms of the components of y. What is x prime in terms of the components of y? That's just y3. And y prime, that's just y4. X double prime, that's 1 over, I don't have enough space for this, do I? That's 1 over m times negative 1/2 times rho times c d times s, pardon me, times the square root of y3 squared plus y4 squared times y3. And then y double prime is 1 over m negative 1/2 rho c d s square root of y3 squared plus y4 squared times y4. This is the same thing. I have written down the exact same thing. I have the derivative in terms of the components of y. Notice there's nothing over here that's not allowed to be in here. What's allowed? We can have x, y, x prime. Maybe I'll write it in terms of y. Let me say this. y1, y2, y3, y4, and t are allowed. And that's all that's in here. Things I know, and y1, y2, y3, y4, and t. Keep in mind that that's actually x, y, x prime, y prime, and t. So, this is a vector differential equation. When you solve a vector differential equation, let's talk about a differential equation. Given y prime is some function of t and y, which is exactly what we have. We know the derivative of y in terms of only time and itself. If you're given this information, then a solution requires an initial condition. Y at some, I'll say y at t naught, and gives y of t in general. It gives you all the values of y at any time. Given what we made y, what our solution is going to be is all four of these quantities as functions of time. That is x, y, x prime, and y prime. X, y position, x, y velocity. From what we're interested in, I probably only really care about position. I want to plot the trajectory, so I'm actually not even going to look at the second two elements of the solution. I'm just going to look at the first two elements, which give the position. So, with that in mind, we need to now talk about how to use Matlab to get results here. Unfortunately, well, I'll just say right now, I'm doing all this work on my iPad and I cannot do Matlab code on my iPad. I am looking for a way to code this stuff up and record the screen on my computer. The only thing I have the screen recording stuff on, oh, I should say, the only stuff I have Matlab on is the remote desktop and my work computer. I cannot install any recording software on my work computer in any reasonable amount of time. So I'm going to have to find a way to do this on my personal computer, maybe by recording the remote desktop, and I'm looking into that. In the meantime, let me just describe what we would have. I would make a function of t and y, which is going to be a vector, and it's going to be rather involved. It's going to have all this stuff in it. So it's going to be y3, semicolon, y4, semicolon 1 over m times all that stuff, comma 1 over m times all that stuff, minus mg. This function is simply this function written into Matlab. Okay, you can see the first two elements are y3, y4. You can see that it's a column vector, so I'm using semicolons rather than commas. Whoops, except for this one, that's a comma. Let's make it a semicolon. All right, and I'm just literally copying this stuff into Matlab. To be able to do this, we need the value for 1/2 times CD times rho. That's the stuff that's out in front. Oh, times S, I suppose. I forgot the S. And you can try and look all this stuff up for a regular shape. I will say for my problems, I just called this C and assigned values to it. And then I changed the value of C to see what generated what looked like normal motion to me. If C is very small, then you'll have just normal projectile motion, a parabolic path. And as C gets bigger, you will see things change. Ha! See things change. Anyway, we need that. So this is equal to C, and I'm going to assign a value and then look at the motion. I'm going to change the value of C in my code and look at different results. So, okay, what do we need? We have the differential equation. We have a value of C. We need to then build an initial condition. Y naught is equal to, I'm going to call this just Y naught in my code. So let me start using like what I would actually say in Matlab. I would call it Y0 equals, I'd have a vector. I'd have my initial position and my initial velocity. I'm probably just going to have it start at x equals 0, y equals 0, because why not? Because why not? Haha, no, that's not funny. All right, and then I want to do x and y velocity. I'm actually curious to give this an initial x and an initial y velocity, so I am going to write this in terms of the initial speed. Let's call this v naught. I'll say, 35, and the initial angle at which it's shot from, I'll say that this is like 30 degrees. And then I will say that y naught is therefore 0 for x, 0 for y, v naught times cosine d theta for the x component, and v naught times sine d theta for the y component. So this is my initial y, and now I just need to hand this off to the real brains of the operation, ODE 45. So I'm going to create two outputs. I'll just call this t and y because I've got no reason not to. This is equal to ODE 45. f, I need to give it the time span. I'll just go from t equals 0 to t equals, I don't know, 5, and let Matlab choose the spacing. You can enhance or extend that time span if you're interested. And I need to give it its initial y value, which is y naught. Please notice this is going to output a many row by 4 column result because it's giving you all of these, well, not those, all of these as a function of time. X, y, x prime, and y prime. I think it's convenient to therefore go ahead and say what x is. X is y colon comma 1. Y is y colon comma 2. This is the x and the y position. Notice if you make this change, you no longer have access to the original y matrix anymore, which honestly to me is fine. The only thing I lost was the x velocity and y velocity, and I don't care. I don't care to see those, so it's fine with me. So what I'm going to do now is, after I'm done with that, we can just plot x versus y, and this will be the trajectory. This will show how it moves through the air. I strongly recommend that you put in an axis equal command so that you have a valid viewpoint for what it looks like. What axis equal does is equal spacing for x and y. That way, if this represents 1 on the x-axis, then an equal distance will represent 1 on the y-axis. And that's important, because if something's shot at a 45-degree angle, it should look like it. If it looks like it's being shot at a 45-degree angle, but the scaling is such that the x-axis has a spacing of 2, then this isn't a 45-degree angle. It's the inverse tangent of 1/2, whatever that is. This angle needs to be, well, I'll just say we want things to look right. For things to look right, we need to have an equal axis spacing, and this is the command to achieve that. So anyway, this would give us trajectories of results. Personally, I would go back and change the value for C if it looked weird. Please keep in mind that this model has no awareness of a ground, so after y is negative, it just keeps falling, and that's fine. Just imagine that it was shot off of an airplane and you're looking at the plot of the trajectory over time, okay? Shot upwards out of an airplane and it shoots up and then eventually falls down. This model does not account for the variation of the acceleration due to gravity as you move up and down away from the Earth, but that's not important. Provided you're not going many kilometers up above the surface of the Earth, or your change of position isn't many kilometers, then it would have no reasonable impact on the solution. So I wouldn't worry about it. However, I would point out we could worry about it and add that to the solution because the acceleration due to gravity depends only on y, and y is allowed. Things in here are allowed to depend on y. So if we wanted to add into the fact that g depends on y, we could do it if we wanted to. Wouldn't change our plot by any measurable amount, so I'm not going to go to the trouble. This is not the problem I asked you to solve. This is not the problem I asked you to solve for problem 4, but you need to understand how to take a physical problem and write ultimately the function, the differential, oh my gosh, I'm struggling here. The differential equation. You need to know how to take a physical description of equations, which look like this essentially, and write them so that Matlab can solve it. And that's the underlying issue. I'll say a couple more words about problem 4. Or, sorry, I don't know if it's problem 4. It might be problem 5. We'll just say the last problem on take-home. You are mostly copying. Almost all of the work, you are not deriving the physical situation. You are simply taking all the equations I have given you and putting them in a function file in Matlab. The important thing to remember is if you must build a function, you must build a function that, if given position and velocity, oh my goodness, of each mass, the function returns velocity and acceleration of each mass. I want to elaborate on that with the example we just provided. That is exactly what we just did. We built a function, that's this one here, where if you give it y, which is the position and velocity, it outputs y prime, which is the velocities and accelerations. Finding the velocities is not challenging. They were already in the original y, so that's not a trick. Finding the accelerations depends on the actual differential equation, and that's got more to it. For this problem, I want you to do exactly the same thing. Most of the challenge is in building that function, but that's what those equations I've given you are all about. If given the function, can you find the differential equation? I hope so. All right, feel free to come and talk to me if you have any more questions about it. I'm going to post a little bit of code. I'll say a video where I build the code to Canvas as well. That's my hope. So keep an eye out for that. All right, everyone. I will see you later.